The invisible forces that hold the universe together? Now, that's a question that could keep you up at night, but don't worry, we're here to delve into the intriguing world of nuclear forces. Nuclear forces are like the unsung heroes of the universe. They're always working behind the scenes, holding everything together. But we rarely give them a second thought. These forces are one of the four fundamental forces of nature, along with gravity, electromagnetism, and the weak force. They're the glue that binds the universe, the secret sauce that makes everything work. There are two types of nuclear forces, the strong and the weak. Much like their names suggest, the strong force is stronger and the weak force is weaker. But that's not where the differences end. The strong force, as the strongest of the four fundamental forces, is like the big brother of the nuclear forces. It's incredibly powerful, responsible for holding the nuclei of atoms together. Without the strong force, protons and neutrons wouldn't stick together and atoms would fall apart. Imagine a world where everything is constantly falling apart. Not a pretty picture, right? That's how important the strong force is. On the other hand, we have the weak force. Now, don't be fooled by its name. The weak force may not be as strong as its counterpart, but it plays a crucial role in the universe. It's responsible for radioactive decay and nuclear fission, processes that are essential for life as we know it. Together, these two nuclear forces play a vital role in the universe. They're like the yin and yang of nuclear physics, each with its own strength and purpose. Imagine the strongest force in nature. That's the strong nuclear force for you. In the world of atomic particles, the strong nuclear force is the superhero, the titan amongst the minuscule. It's the force that binds protons and neutrons together in the nucleus of an atom. Protons, with their positive charge, would naturally want to repel each other, but they don't. They stay together, huddled in the nucleus. Why? That's the power of the strong nuclear force. This force is like the superglue of atomic particles, holding the nucleus intact. Without it, the universe as we know it wouldn't exist. No atoms, no elements, no stars, no planets, no life. The strong nuclear force ensures that our universe remains coherent and structured. Now, how strong is the strong nuclear force? Well, it is about 100 times stronger than electromagnetic forces. That's right, 100 times. It's like comparing the strength of an ant, capable of carrying objects 50 times its own weight, to that of a human. Seems unimaginable, right? But that's the reality in the world of atomic particles. Yet every superhero has its kryptonite. For the strong nuclear force, it is its range. While it might be the strongest force in nature, its influence is curtailed. It can only reach as far as the size of an atomic nucleus. Beyond that, its power wanes drastically. So while it can keep protons and neutrons in check within the nucleus, it cannot exert its influence on the electrons orbiting far from the nucleus. This is a fascinating aspect of the strong nuclear force. Immensely powerful yet confined, it's like a lion in a cage, mighty and fierce but limited by the bars that surround it. So that's the strong nuclear force, immensely powerful but with a limited range. This force, in all its might and limitation, plays a pivotal role in the grand scheme of the universe. It's the force that shapes our reality, orchestrates the symphony of the stars, and makes life possible. Now, let's step into the realm of the weak nuclear force. This force, though not as famed as its strong counterpart, is a bit of a dark horse in the universe's grand scheme. The weak nuclear force is one of the four fundamental forces of nature, and it's responsible for some pretty impressive feats. Let's talk about radioactive decay. Ever wondered what's going on inside a radioactive atom? Why does it spit out particles and energy? Well, that the weak nuclear force is the prime mover behind this. It's the force that causes certain kinds of subatomic particles to transform into others, a process known as beta decay. During this process, a neutron in an atom changes into a proton, an electron, and an antineutrino. Fascinating, isn't it? And then there's the fusion process that powers the sun. This process wouldn't even start without the weak nuclear force. It's the weak force that allows protons to overcome their mutual repulsion and fuse together, releasing energy in the process. So in a way, the weak nuclear force is the reason we're not freezing in the dark. Now you might be wondering why it's called the weak force. Well, its strength is 1,000,000 times less than the strong nuclear force, but don't let that fool you. Despite its name, the weak nuclear force is not weak in any meaningful sense of the word. In fact, it has a range that's slightly more than the strong nuclear force. Although its range is still very short, it's enough to have a significant impact on the nature of matter at the subatomic level. So, the next time you're basking in the sun's warmth or marveling at the glow of a radioactive substance, remember the subtle yet powerful weak nuclear force. Though it might not get the limelight, it's silently shaping the universe as we know it. Though weak, this force plays a crucial role in the universe. Now, we've explored both the strong and weak nuclear forces. It's been quite the journey, hasn't it? We've delved into the heart of the atom, where these forces reign supreme. So, let's take a moment to look back and summarize what we've learned. The strong nuclear force, as the name suggests, is indeed powerful. It's the strongest of the four fundamental forces of physics, but it's also a bit of a homebody. It prefers to stay close to home, acting over a very short range. It's like the bouncer at the entrance of an exclusive club, keeping the protons and neutrons tightly bound together in the nucleus of an atom. Without the strong nuclear force, protons with their positive charges would repel each other, and the nucleus would simply fall apart. On the other hand, we have the weak nuclear force. It might not be as strong as its counterpart, but don't let the name fool you. This force has its own unique capabilities. It has a slightly longer reach than the strong nuclear force, and it's responsible for some pretty important phenomena. You see, without the weak nuclear force, certain types of radioactive decay wouldn't occur. This force also plays a key role in nuclear fusion, the process that powers our sun and the stars in the night sky. So, to sum up, we have the strong nuclear force, the muscle that holds the nucleus together, and the weak nuclear force, the maestro orchestrating radioactive decay and nuclear fusion. Each force, in its own way, is essential in maintaining the balance and structure of the atoms that make up our world. These two forces, though vastly different in strength, play a significant role in the intricate workings of our universe. As we reach the end of our journey, let's ponder over how these forces shape our universe. The strong and weak nuclear forces, seemingly invisible yet so potent, are the very framework of our existence. They play an essential role in the fascinating realms of science, from the generation of nuclear power that lights up our cities to the understanding of the life cycle of stars that light up our night sky. By comprehending these forces, we don't just unlock the secrets of the atomic world, but we also gain insights into the very fabric of the cosmos. They are the unseen puppeteers pulling the strings of the universe, choreographing the cosmic dance of particles and energy. They are the silent architects shaping everything from the smallest atom to the most colossal star. The next time you look up at the stars, remember the powerful forces at play, the strong and weak nuclear forces.